I've been fascinated by the swirl of the Milky Way galaxy ever since I saw it in my toddler storybooks, which further on went to being imprinted in my primary school textbooks and then in those I received during my high school. After researching for days, I started understanding the fundamentals of the space. I knew that various telescopes already exist in the space to calculate the infrared radiations, cosmic microwave background radiations, Hubble constant, and various other values that impact the geometry of the universe. So I gathered the values for the constants I required from the original research papers of these experiments and calculated the value of the constants I could not find by placing the value of the other constants in the standard formulas. The very fabric of space-time itself is a physical manifestation of quantum entropy concepts woven together by the universal nature of location. The geometry of space itself is one of the most massive and peculiar mysteries in the universe. However, we do know that space expands. In cosmology, the terms spherical, hyperbolic, and flat refer to various geometries of the universe. Now, one might ponder if the universe is spherical, hyperbolic, or flat. Space can bend due to energy and matter, curving the paths of objects that move inside of it. The discovery that galaxies are moving away from one another with the distance between them increasing over time, as demonstrated by the redshift of light from distant galaxies, represents the universe's expansion. All of these phenomena can be described by the curvature of space. Friedman, Robertson, Walker, and Lemaitre independently came up with a simple yet powerful model to quantify the expanding universe. The FLRW model indicates that the universe is homogeneous and isotropic. In cosmology, homogeneous universe has the same composition and properties at every point, while an isotropic universe looks the same in all the directions. 16 of Einstein's field equations describe how mass energy behaves in space-time. Now, let's explore the equations referring to the FLRW model. In the first equation, G is the gravitational constant, whereas ρ is the volumetric mass density. And from here, I shall be deriving the Friedman equations further on. The second equation on this slide describes the energy density of radiation throughout the universe. Radiation density falls with the fourth power of the scale factor, that is A within bracket T. This rapid decline reflects the fact that as the universe expands, the wavelength of the radiation lengthens, resulting in a fall in the energy density. The radiation density parameter is denoted by omega r, the Hubble constant by h0, and the gravitational constant by g. The equation after this on the slide describes the energy density of all the stuff possible in the cosmos, including the dark matter as well as the baryonic matter. Matter density falls with the third power of the scaling factor, that is A within bracket T. Matter dilutes only with volume growth, not with the added redshift factor, which explains why it decreases slower than the radiation. The matter density parameter is denoted as omega m. The next equation, which refers to the negative pressure, describes the energy density of dark energy, which is constant over time. Dark energy, which has negative pressure, is responsible for the universe's accelerating expansion. Unlike matter and radiation, dark energy does not dilute as the cosmos expands, as indicated by the constant energy density. The dark energy density parameter is denoted by omega cap. Finally, we get the Friedman equation, which is the last one on this slide, by plugging in the values discussed earlier. In this equation, rho cap naught is the energy density in the vacuum, rho m naught is the energy density in the non-relativistic matter, rho r naught is the energy density in the relativistic matter. A matter moving at speeds close to the speed of light, requiring the use of Einstein's theory of relativity to describe its behavior. Out here, c also represents the speed of light, and k is the curvature of the parameter. Now, let's have a look at the curvature of spacetime, which plays as a factor in determining the geometry of the universe. Substitution of varying values of k in the Friedman equation represents the curvature of the universe. Values of k can be plugged in as positive 1, 0, or a negative 1. The following images in the slide depict how a rocket and an alien ship would trace their path in different universes with varying shapes. Following are the experiments that validate curvature of the universe. While researching, it can be noted that experiments like Planck, Bose, WMAP, and DESI have presented Hubble constant in the range of 66 to 70 kilometers per second per megaparsec, whereas experiments such as Pantheon SH0ES, MCP, and Hubble Space Telescope have proposed Hubble constant in the range of 73 to 74 kilometers per second per megaparsec. Continued progress in improved sensitivity, futuristic upgrades to observatories like Simon's Observatory, CMB-S4, and Vera-C are playing a crucial role on this planet. Through constant development, the scientific community shall make strides in resolving uncertainties and uncovering the geometry of cosmos with more intricacy. All in all, in this research paper, I examined different values of Hubble constant and how it affects critical density and geometry of the universe. I also studied the varying values offered by the 8 experiments on the previous slide to compare their similarities and intricacy. Thank you for paying attention today. I hope you liked delving in the geometry of the universe as much as I did while unraveling it.